Welcome. Go ahead, Chris.
Okay. All right. Welcome, everybody. Welcome to our 5 Steps to a 5 webinar for AP Physics 2. I'm Chris Bruin, and I'm glad you're here. We're going to go ahead and get started so we honor everybody's time. And so we start and end on time. So I'm going to hand this over to Bob O'Sullivan for just a little bit. He's going to talk us through a few of the background for this presentation.
Thanks, Chris. Hello, everybody. I'm Bob O'Sullivan, Associate Publisher of Test Prep at McGraw-Hill. Just a couple housekeeping items before we get underway. If you see the slide here, just so you know, we do welcome both educators and students, teachers and students, to the presentation, but we do design this to be primarily a student-focused review. We're about, 6, 7, 8 weeks out from the test now, so we do think it's valuable to focus on the students, but both teachers and students are welcome. If at the second bullet reads that we prefer that you save your questions until the end, we've decided against that. We're not seeing that many, the attendance numbers have not been so astronomical that we're having a problem keeping things organized. So please, if you do have a question as Chris goes through his presentation, please feel free just to put it in the chat or the Q&A. Either way, we'll do our best to answer it quickly after you ask. If you get in there and somebody has already asked the same question as you have, just take that question and put the thumbs up icon so we know it's an important one. A note that you guys will not be able to see one another. You should be able to see me and Chris and hear both of us. And I think you should be able to hear the other 2 people on the line, Anya and Simone, also from McGraw-Hill. So if that's a problem, let us know, but you won't be able to see one another. And an important note on student data, no student data is being collected, right? If you're a student, if one of your students is on this call, we're not collecting any data, so you don't need to be concerned about that. We do hope that you will participate in any interactive features we have as we go through. There'll be some practice questions and polling that comes up. We would hope that if you see the polling and you want to answer the questions, we urge you to do so. It makes it more fun and more engaging for everybody. And perhaps most importantly, the session is currently being recorded. That bit.ly, that URL at the very bottom, if you want to just take a second and take a picture of that with your phone, give it a few seconds, but we'll show it again at the end of the presentation. But as of tomorrow, we should have this recording should be live, and that's the URL that you'll access. So welcome again. I'm going to hand it back over to Chris. Chris, over to you.
All right. Awesome. Thanks, Bob. Well, welcome to you, those of you that are here live, and for those of you that will be watching it recorded. Our agenda for today is real straightforward. Just a real quick intro to me, and then the subject at hand. I'm going to give you some test taking, course and exam info about the course AP Physics 2, and then some general tips about taking the test in general. Some things that will help to maximize your score and help you to feel like you're going to be more successful. And then we're going to talk about one of the topics, our biggest topic in AP Physics 2, which is electricity and magnetism, that grouping. We'll talk a little bit about the content real briefly. It's not gonna be like a lecture or anything, but just kind of a review of the things that you've learned in class to help you remember. And then we're going to go through the content a little bit at a time, and then have like a multiple choice question to go along with it from the 5 Steps to a 5 book, to kind of give you an idea of the things you need to remember for the test to be successful, but also the things that are in the book to help you to be successful. So, and then we'll have question and answer at the end if we have any burning questions. So usually there's some. All right. So I'm Chris Bruin. I've taught AP Physics for a long time. I was an aerospace engineer before I became a physics teacher. And so I've taught all the different versions of physics, but my favorite is AP Physics 2. It is a lot of fun. I like the content in AP Physics 2. It's a little more broad, and I think we get more hands-on stuff, which is fun to do. Anyway, I've written some books, including 5 Steps to a 5. I'm an AP consultant and reader. I'll be, for those of you that are going to be taking the test, I'll be reading your questions or your responses on the free response and helping to grade them this summer. And then I'll also be recording some of the videos, the new videos that you'll see on AP Classroom.
Quick note, Chris, I forgot that was the cover. I don't know if you've seen that yet, the new cover of the book.
Yeah.
Actually, I forgot that was our cover. It's a really cool image.
Yeah. So that's a little bit of a magnetic fluid over here. So you can see the magnetic field lines from the magnetic field, which is pretty cool. And anyway, so I do this sort of thing with those of you that are watching online live, or those that are watching the recording for students all over the country. So I hope I'm helpful for you, getting you ready for the exam. All right, so let's talk a little bit about the AP Physics 2 course and exam specifically. Okay, first thing, the most crucial thing is when you're taking the test itself is to remain calm, relax, okay? Here's the big thing, is you're not supposed to get all the questions right. So all of you that will be taking the AP exam, you're all bright, you're all very smart individuals. Some of you have more skills in one area than another, but there's no doubt that you're all very intelligent. And the test has a way of making you feel not intelligent, okay? It's designed that way so that they can spread out the bell curve, so that they can tell the students that kind of really know it really, really well, the ones that know it well, the ones that are growing in their knowledge, but have gained a lot of knowledge and success and skills in physics, and those that are still kind of working towards that level. So the test is not designed for you to get 100. So not if, but when you run across, I'm sorry, not if, but when you run across a problem on the test that you don't know how to answer, don't fret, don't worry about it. It's going to be okay. You're not supposed to get them all right. Okay. So what's needed to pass the exam? Passing. All right. So to get a 5 on the exam, you need about 3/4 of the questions correct. That's about a 75%. To get a 4, that's the best score you can get. Okay. So really, they expect the very best students to miss a 1/4 of the questions. Okay. To get a 4, you need about a 2/3, or about a 66, 67%, somewhere in that range, roughly. Changes a little bit from year to year. And to get a 3, you need about half the questions correct. All right. So when you come across one you don't know how to do, just skip it, come back to it. Only go through the test the first time through and work the ones that you are comfortable with, that you feel confident in, and that you're sure you know how to do. Work all those first, and then come back, circle back around and start working the ones that you think you know how to do, or it takes more time, or you have an idea. All right, write down the things that you know if it's a free response. Don't ever leave anything blank. And on the multiple choice, take your best shot. And if there's anything left at the end, don't leave anything blank. Never, ever leave anything blank, because on the test, you only earn points. You don't lose points, okay? So if you don't write anything down, you guaranteed yourself a lower score. So always give it your best shot. If you're not sure, but you say, well, I know that energy is conserved in this situation, then write down energy is conserved, and then try to apply that idea and see what you can do. Because the points really aren't awarded for the correct answer. They're awarded for you showing your knowledge that gets you to the correct answer. Okay. So if you don't show that you know, hey, conservation of energy applies here, you don't write that down, the reader won't know. And so they can't award you any credit, which is always sad, because we want you to do well on the exam. We really do. Okay. But we can't give you points. if you don't show us what you know. So please always write down as much as you can that you think you know applies in a particular problem. All right. So don't stress out. Work the problems you know first, and then circle back around and do the rest. Okay. Next, let's talk. Next, let's talk specifically about multiple choice questions. The multiple choice questions section has 50 questions. There are 45 standard multiple choice questions and 5 at the very end that are pick 2. Now, these are unusual, unique, I think, to the physics exam. And so you have to pick 2 answers. They have to be the exact correct answers. If you pick one that's incorrect, or if you don't pick 2, then there's no partial credit. So you have to pick the correct 2. A lot of students really get psyched out by those, but they're usually more wide open conceptual questions. So they're not really any harder than any of the other ones. My students historically have done just as well on the pick 2 as they have on the regular multiple choice questions. All right, so don't let them intimidate you. You have 90 minutes. That's 1.8 minutes per question. So a little less than 2 minutes per question. All right. Some of them you'll answer really quick. Some will take longer. All right. So again, answer the ones you know how to do first. Make sure even if that's just 10, you go through all 50, you can answer 10, answer those 10. You've just guaranteed yourself that you've gotten to those. What we don't want is for you to start working the really hard ones that you don't know what to do with. They're like something maybe you didn't get to in class, or maybe that's just always found difficult. Don't waste your time on that question. Make sure you answer all the ones that you know how to do first. And then at the end, go back and do that question, because we don't want you to run out of time. Okay. Don't leave anything blank. There's no guessing penalty. All right. And absolutely don't look for a pattern. Okay. Sometimes students will come out of a test and they'll say, oh, Mr. Bruin said, I answered the first 10 questions D, and I was all freaked out because the next question that I thought the answer was D as well. And I remind them, I'm like, look, did you get all of those correct? And they're like, oh, probably not. And I'm like, yeah, so why are you looking for a pattern? There's no pattern. Sometimes the most popular answer on a test is D. Sometimes it's A. It's not always C. So just answer each question individually to the best of your knowledge. So let's look at a couple of more hints to improve your skill on the multiple choice. One thing that's super important, I think this helps a lot of students, is that the questions get very wordy. So the one you see on the screen right now has a lot of words, and your brain starts to fuzz over as you get halfway through, and you're not even sure what you're supposed to be reading and looking for. So the last sentence in the stem of the question, I've highlighted up here in yellow. That's the question. So if you read that first, you'll start to understand what you're looking for. So if you just start at the top, 2 sealed cylinders holding different gases are placed one on top of the other so that heat can flow between them. Cylinder A is filled with hydrogen. It's like, oh my gosh, already you've got brain overload and you don't even know what you're looking for. So read the highlighted part first. Read the last sentence first. Which of the following best describes the transfer of heat between 2 containers by conduction? Like, oh, so I'm looking for heat transfer by conduction. So not radiation, not convection. So I'm looking for heat transfer. And I'm like, wait a minute, I know that heat transfers between 2 containers or 2 objects from hot to cold. So whichever one has a higher temperature, then heat will flow from high temperature to low temperature. So now I have an idea of what I'm looking for as I read the question. Okay. So that helps us out tremendously, so that we know what we're looking for. We don't waste a lot of time. All right. So in this particular one, you have 2 cylinders. One's filled with helium, one's filled with hydrogen. And then it says the helium is moving at an average speed that is half of the hydrogen atoms, but the helium has 4 times the mass of the hydrogen atoms. So what we're going to try to do then is since we know we're looking for heat transfer by conduction. We're trying to see which one has a higher temperature or if they have the same temperature. In this particular case, they have the exact same temperature. So answer choice C is our correct answer. There's no heat transfer between the two cylinders because they have the same average atomic kinetic energy, same temperature. All right. Another key thing to do, and I encourage you to practice this before you walk into the exam. So like when your teacher gives you multiple choice questions, practice looking for the wrong answers. All right. And cross off the ones that cannot be correct. All right. And then choose what's best from what's left. So even if you have to, you're not sure of your answer, at least you have you're taking an educated scientific guess instead of just a random guess, which is a much better chance of doing well. So in this particular case, it says we have a mirror. I'm sorry, I didn't even follow my own guidelines. What is the focal length of the mirror? So read the last sentence first. Okay, so I'm looking for focal length. All right. Now it says a mirror produces an upright image that's 1/2 the height of the object. Okay, stop right there. We got a mirror. We're producing an image that's upright. So since it's upright, it must be a virtual image and it's half the size. So virtual, half the size. What kind of mirror does that? And it's like, wait a minute, that is a mirror that is, that's convex mirror. It has a negative focal length. So I know my answer has to be negative focal length already. So I can cross off C and D. And then even if I mess up the math, I've got a much better shot because I know my answer has to be negative. All right. So our answer in this case actually turns out to be negative 12 centimeters. All right. So read the last sentence. Make sure that you cross off the ones that have to be wrong first. Always look for wrong answers that you can cross off. All right. Next thing is in multiple choice. If they show you a figure or a picture or a diagram, there's going to be information there. And so always look for information in the picture or diagram or graph. And most of the time, the information is somewhat hidden. You have to be able to interpret what's going on. Okay, so like in this particular case, what is the resistance of the resistor? Okay, but up top, they give you power versus voltage and power versus voltage squared. All right. So I'm looking for resistance of a resistor and they're giving me graphs. Okay, so what are my equations for power? Well, in circuits, power equals current times volts, or, but I don't have current on this graph. So I have volts and volts squared. Hey, power equals voltage squared over R. So I've already written that down. And so, hey, look at this. Power as a function of voltage squared, it should be linear. And the slope should be 1 over R. Okay, this is one of these linearization questions that show up on the test where you have to be able to turn a graph or an equation that won't be linear into something linear and then interpret what the slope is. Okay, so in this particular one, the resistance of the resistor will be the slope will be 1 over the resistance. Okay. So in this case, if we look carefully, looks like our slope is approximately from 0 to 4. So rise of 4 over run of about 80. Okay. So that's 1 over the resistance. So when we flip that over, we get 80 over 4. So the answer should be 20. Okay. All right. So on these graphs, they rarely give you a graph where you can just pull information straight off the graph. Usually you're going to need to find the slope or the area or the intercepts or read something from the graph and manipulate it somehow. Okay. But it always has info you need. All righty. Let's see. Let's talk about free response questions. There are 4 free response questions. You also have 90 minutes for the free response. And 2 of the free response will be longer than the other 2. The 2 that are longer are the lab-based question, where you have to design a lab usually, or maybe also interpret lab data that's given to you and then manipulate it or do something with it, like answer a question based on the lab data. Okay. There's also this thing called a QQT problem, which is a qualitative quantitative transition problem. It's a very fancy name for, they're going to ask you some qualitative questions and then some quantitative or graphical or algebra type questions about the same topic, and see how those two ideas mesh together. Okay. And then the 2 shorter ones will be a paragraph argument and then a short answer one. So let's talk about the 3 unique ones, the top 3 up here, in a little more detail. So on your lab-based question, okay, most students, most of the time you're asked to design a lab, and most students design a lab that's too complicated. Keep it simple, keep it elegant, keep it as bare bones as possible. Okay. You don't need to do something super fancy. Okay. It's got to be something that you should be able to accomplish. Any student in the United States should be able to accomplish in a physics laboratory with, you know, bare bones, basic equipment. All right. So, you know, like if you're in gas laws or thermodynamics, you'll have temperature, you'll have a pressure gauge. All right. You know, if you're in electricity, you'll have a voltage meter or a multimeter and an ammeter. You know, we're talking basic equipment. All right. So you don't need to invent anything special. Don't invent a piece of equipment that measures something that you haven't actually done in your own labs, usually because maybe that device doesn't exist, right? So just basic equipment is all you need. Okay. So when you're trying to design and design a lab, first and most important is make sure you understand what the lab question is. Okay. Every year when we're grading these questions, it breaks our heart because a student clearly knows what they're doing. They have lots of knowledge in their brain and they're expressing themselves well on the test, but they didn't answer the lab question. Okay. So like one year, there was a question about you are to design a lab to show the relationship between, say, pressure and temperature of a gas. Okay. And what we got were a lot of students would just start writing out, hey, pressure is directly related to temperature, because they knew that PV equals nRT. They already knew the ideal gas law. And so they started writing out all this stuff they knew about pressure and temperature and how they were related. The only problem was they didn't answer the question. The question was design a lab to show the relationship between temperature and pressure. And so that means the students needed to somehow show that they could change the temperature of a gas and then measure the pressure change, and then take that data and represent that data to show the relationship between the two. Okay. So make sure you understand what the lab is asking you to do and make sure you answer that question. Okay. So make sure you understand your task. Always write down the basic physics principles you'll be using. Okay. So like maybe you're using Kirchhoff's rules in electricity, or maybe you're using the ideas in magnetism about magnetic field around a wire. Okay. Write out the equation that you're going to be using. Okay. Because the equation that you're going to be using to help you in the lab is going to tell you what equipment you'll need. Okay. So if your equation has like voltage and current in it, then that means that you're going to need to have a voltmeter and you're going to need to have an ammeter. Okay. So write out the equation of the basic physics principle that you're going to be using to help you design your lab. Okay. Make sure you write down what equipment you're going to use and what and what you're actually going to measure. So like I'm going to use a voltmeter to measure the voltage around resistor number 1. Okay, I'm going to use an ammeter in the wire to measure the current that's going through resistor number 1. Okay, make sure you spell out the equipment and what you're going to measure. All right, and then write your step-by-step procedure. I always tell my students to write it in number format, 1, 2, 3, 4, 5. So they kind of think about what comes first, what comes second, what comes third. All right, and then always in your lab, have a little sentence in there about what you're doing to reduce error, because one of the points on the test is usually about, did the student address reducing error in the lab? And the question usually doesn't ask you to do that. They just expect you to know that you're going to try to build a lab that's going to be accurate. So just tell them what you're going to do. Like you're going to measure it 3 times and average your results. You're going to use a certain piece of equipment to help you measure it more accurately. Just tell them a little blurb about what you're going to do to reduce error. Okay. All right. This QQT problem is one that a lot of students hate. It's really not that bad of a question, but it does give some stress to students. So let's kind of run through what a QQT question might look like. All right. A lot of times on these questions on the free response, there'll be something that you've never seen before, or it's like something that's really unusual. But remember, whatever they ask you about, it's still going to be something in physics that you've learned. All right. So it's either going to be fluids. So all of our ideas about fluids that we learned, or it's going to be about gases or thermodynamics or static electricity or circuits or magnetism or waves and optics or quantum atomic nuclear. It's going to fall into one or multiple of those categories. So even though what they write down in the problem may be something you've never seen before, all the stuff that we've learned will be able to solve it. Okay, it's something that falls into one or more of the categories of what you've discussed in the topics of AP Physics 2. So a QQT is a classic one where they give you something weird, and then they ask you questions about it. All right. So the qualitative part a lot of times is a ranking task or a comparison task, or they'll say, hey, I'm going to change this value. What happens to this other value? And they ask you just qualitative questions. And then they'll ask you to sketch an accurate graph, or to derive an equation, or an evaluate an equation that they give you and say, does this match up with what you think to be true? All right. So let me give you an example. Okay. So let's say that we have like a battery, and this battery has a resistor, just a single resistor. So this battery has a voltage of EMF, and this has a resistance of R. Okay. And let's say that they bury this inside of a container, okay, that's filled with gas. All right. So that they can flip the switch, turn this thing on, and this is going to heat up the gas. All right. And so they tell you this thing starts with a pressure of P0 and a volume that's fixed. Okay. And then they tell you that there's a certain number of atoms inside here that's fixed. So it's a closed, fixed container. And then it starts off at a temperature 0. Okay. Or a temperature 0, sorry. And then they ask you a couple of things. They ask you, what happens to the pressure? Oops. What happens to the pressure if we increase the voltage? Okay, so we're going to, number one, we're going to increase the voltage of the battery. What's going to happen? Or they say, what if we to increase the resistance, right, of the resistor? Okay, and so then they'll say, all right, what do you think is going to happen to the pressure? And then give me your answer. So like, okay, well, as the voltage goes up, I'll get more current, right? More current will run through the resistor, so I should generate more heat. And so therefore, as the temperature goes up, the pressure should go up because the volume is fixed and I have a fixed amount of gas. Okay, so I'm going to predict that the pressure goes up as well. All right, then I verbalized it, but you have to write out why you think that is. Okay, and then the resistance goes up. So if the resistance goes up, then, hey, if the resistance goes up, the current would go down. And if the current goes down, then the opposite would happen, right? I'd have less heat generated. And if less heat is generated, then I should get less pressure because PV equals nRT. So the temperature won't go up as much. So I should have less pressure increase. All right. So the pressure will go up, but I'll have less pressure increase. All right. So that may be a question like that, where you change one variable and then you see what it does to another variable. Okay. They may ask you something like this. They may say, okay, well, how about, why don't you sketch what the pressure will be like versus time? So let's say we close the switch, we let this thing run and run and run and run. What's going to happen to the pressure as time goes by? And you're like, oh, well, we started off at a pressure, E naught, and as time goes by, I'm going to generate more and more heat, which should make the temperature go up, which should make the pressure go up. And it looks like it's going to go up something like this. Maybe it's linear, maybe you don't know, but you know it's going to go up. So they're going to look to see, did you have a good intercept? Do you show the right kind of relationship going up? And then they will also check for the curvature if the curvature is important. Okay. So they're looking for things like that. Or in this question, they might add on something like this. They'll say, hey, a student has derived an equation where they say the pressure as a function of time equals the EMF of the battery, the current, and the time divided by the number of atoms and the volume. Okay. All right. So this is a student came up with this equation somehow. And they tell you, does that make sense? Or they ask you if that makes sense. Well, what they're looking for in a question like that is they're looking to see, do the things in the numerator make sense? And do the things in the denominator make sense? Like, for instance, does it make sense that time is in the numerator? As this thing runs longer and longer and longer, should the pressure go up and up and up? And it's like, yeah, that looks good. So that one looks good. So we'll put a smiley face next to that one. Does it make sense that as the voltage goes up and this thing runs, that I should get more pressure out as I get more voltage? And that's what we set up here, right? So that makes sense. That looks good. All right. And so that's all they're looking for, is check each variable. Does that variable make logical sense? And what we're looking for is, does the number here, does the relationship, is it direct or indirect? Okay. So we're looking for, should it go in the numerator or denominator? They're not really worried about whether it's squared or square rooted or something like that. Okay.
Can I just remind you quickly, we're just past 30 minutes already. We're at 34 or so minutes in.
Okay.
So just a quick time check for you.
All right. Thanks so much. Another thing they'll ask about this is, say, does this equation match up with, say, this graph up here? And this is always a tricky one. So let's see, time is here, pressure's here. So there's the time and there's the pressure. So as time goes up, pressure should go up. So that looks good. The only thing is notice this has an intercept and this over here does not have an intercept. It shows nothing over here for an intercept. So just be careful. That was one that got a lot of students and many teachers on a previous question. Okay. All right. Let's go back to our presentation. When you get a free response problem that is a paragraph argument, the paragraph argument means that it's going to take more than just a simple statement to answer the question. Usually these are 5 to 7 points for your paragraph. So that means you're going to need at least 4 key statements of logical steps in order to be able to answer it. So many of your teachers may have taught you CER, claim evidence reasoning, and that's great. You can solve it that way. There's another one that also helps out. This one actually was developed by a guy by the name of John Frensley, physics teacher, and he calls it ABCD. And it's A stands for answer the question, B says what basic physics are you applying, and C is what critical information is important in this situation, and then draw your argument together. So I use ABCD with my students, and I tell them to just draw a little T-chart like this, and then let me kind of run through it to help you out, see, so you can answer your questions a little bit more clearly. So here's a free response that has a paragraph response. An air bubble is formed at the bottom of a swimming pool and then released. The air bubble ascends towards the surface of the pool. In a clear, coherent paragraph length response, describe any changes in the bubble size and describe the motion of the bubble as it ascends to the surface. Explain the factors that affect the size of the bubble and the bubble's motion. All right. So how would we do that? Let me share my screen here just real quickly again. So I'm going to make myself a nice big T-chart right here. There's where my answer goes, basic physics, critical information, and then my discussion or drawing my argument together. Okay, so I've got a bubble that starts here and it's going to ascend towards the surface. Okay, so I know I've got fluids. So in fluids, I know pressure equals pressure naught plus rho GH. I know in our situation that the bubble is going up. Bubble goes up. Okay, let's see, what other basic physics do I know? I know that there's going to be forces, and there's going to be a buoyancy force. Buoyancy force equals rho VG. I know that in my situation, my bubble has a buoyancy force up and a gravity force down. I know that the force up is bigger than the force down. So I'm going to have a net force up, and therefore it's going to accelerate up. Okay. All right. But the pressure as I go up is going to get less. As the pressure goes less, I know that PV equals nRT for a gas inside my bubble. And so as the pressure goes down for my bubble, the volume of my bubble should increase. And then as my volume goes up, my buoyancy force should go up. Okay, I think I've got what I need now. All right. I know that the buoyancy force is greater than the gravity force. Therefore, the bubble accelerates upward. Okay. I know that the pressure decreases as bubble goes up. Okay. And the volume increases. Therefore, the buoyancy force increases. Excuse me. And acceleration increases. Okay? So my answer then is simply, what was the question? The question was, describe its motion and describe what factors affect its motion. And now I really have my answer, but I always tell my students to just give a one sentence at the top of what your answer is, just so that the reader knows where you're going in your argument. Okay? And so basic physics is the stuff that has to be true no matter what. Notice everything over here is just physics laws that we know are always true. The stuff over here is information about my particular situation, that I have a bubble that's ascending. And then I use these two things to make my argument over here. And then write your answer at the top, and you're done. So I think this helps students focus what their answer is going to be, because sometimes you get a little lost. And anyway, so I hope that helps out a lot. It helps my students a lot. Okay, let's talk about the essential topics in AP Physics 2. So AP Physics 2 has these, 7 topics: fluids, thermodynamics, static electricity, circuits, magnetism and induction, and then geometric and physical optics and quantum atomic nuclear, okay? Of those topics, here is the approximate amount that they'll be on the test, okay? Notice that fluids and thermo and geometric optics and nuclear are about half the test. And the other half of the test is this grouping that we call E&M. The biggest single topic is static electric force and electric field and electric potential. It's going to be about 1/5 of the exam. So make sure you review that before you walk into the test. And then electric circuits, and then induction and magnetism. And so this grouping of E&M is approximately 50% of the exam. And it usually goes together in a big lump in the middle of your school year. And you've probably just finished mechanics and are getting into optics right now. So let's review this big chunk. So all the questions from here on out are going to be in this topic area. So static electricity, remember this is about charges and their arrangement and their movement, and it talks about electric forces, electric fields, electric potential energy, and work, okay? Circuits talks about, in particular, Kirchhoff's rules of conservation of charge and conservation of energy, and how those apply to circuits, which give us our series and parallel rules. And then magnetism, magnetic force, and on moving charges and wires and induction, all right? So let's review a little bit. So let's start with static electricity. Okay, electric charge, here are the first things you'll learn in static electricity. Charge is quantized, meaning it comes in small indivisible bits of electron charge, and they are 1.6 times 10⁻⁹ coulombs. Big thing is charge is conserved. So this charge doesn't just disappear. So the charge we start off with is the charge we end up with. So if charge moves from one place to another, one will gain like negative charge and the other one will lose negative charge, leaving one negative and one positive. This movement of charge is through friction, through conduction or contact, and polarization and induction. And there's always questions about this movement of charge on the test. So let's take a look at that first. Okay, here's our first practice question. This comes off the practice exam number 1 from the 5 Steps to a 5 book on page 302. All right, it says a positively charged rod is brought near to but not touching 3 metal spheres that are in contact with each other as shown in the figure. Which is the best representation of the charge arrangement inside the 3 spheres? Okay. All right, so you'll see a poll has just popped up on your screen. If you will please answer the question as best as you can, and then we'll run through it real quick.
For those watching live, you can toggle, you can click and drag the poll box over the side if it's blocking the question.
Oh yeah, thanks, Bob.
Anytime. I thought I was going to be able to answer the question, but I'm As a panelist, I'm unable. It was going to be a crapshoot, but I was going to try anyway.
All right. So we have that most of you picked D and some of you picked C. So let's think about it for a second. So first of all, these are all in contact. So that means, and they're all metal, right? So charge can flow between them. And we know that positive charges don't move inside of the object. It's the electrons that are moving inside of a metal. And so the positive charges should stay put and only the electrons should move, and they can move all the way across to the left. So our best answer is, there it is, C. Okay, so a lot of you picked D. And this is a purposeful distractor that they'll put on the test. Since these are metals in contact, charge can flow between them. And so the electrons will flow all the way to the left, or some of them will flow all the way to the left. And notice that the protons cannot move. So one of the giveaways that D can't be correct is it shows protons on the right and electrons on the left. Okay. The protons can't move. So you'll notice that in the top three, the protons stay in place. All right. Next big thing in static electricity is the idea of electric force. And you'll see it written different ways. This one's written with 1/4 pi epsilon naught. Remember, that's the same thing as K, the Coulomb's law constant. And notice that this one is written with absolute value signs. I encourage you to solve it absolute value and then decide the direction of the force, whether it's attraction or repulsion. So let's take a look at this question. This one's more mathematical in nature. This is from Practice Exam 1 on page 302 of the book, of the 5 Steps to Applied book. The metal spheres on insulating stands 1, 2, and 3, they're all identical and they're situated as shown in the figure. Spheres 1 and 2 have a charge of -Q and sphere 3 has a charge of +2Q. The force from sphere 1 and sphere 2 between them is +F. What is the magnitude of the net force on sphere 3 in terms of F? You're gonna have to do a little proportional reasoning here.
Take a shower if you're on the call.
It helps if you draw a picture of this and then draw arrows for your forces. Okay. And remember, the force on sphere 3 will be from both of the charges on sphere 1 and 2. All right. So we have the most popular answer was from was B. All right, so let's see how we did. So -Q, and the force between these two would be repulsive, and it would be F. Okay. Now they tell you this one has a charge of +2Q. All right. So now this over here, Q, and D. So the force equals K, Q over D squared, right? And F equals that. Over here, what if we change? So let's just look at these two. All right. So how is the force different here? First of all, it's attractive, so it's to the left. Okay. And then second of all, I've doubled one of these charges. So I've doubled one of them, so the force will be 2F. So very good. If you pick B, you got partly right. But what you forgot was that there is also a force from this one. Okay, so how does that change? So when we take this one out, how does it change? Well, not only did we double the charge, but we also doubled the distance, and that's squared. So that's a 2 over a 2 squared, which means that's F over 2. So the force between these two will be F over 2, and it's also attractive. So it's F over 2. So I've got 2.5 F is the net force. So if we go back, that answer would be 5/2 F. Okay. So a question like that is definitely going to take longer on the multiple choice. So if you see one like this and you're like, that's going to take me too long, just skip it and come back to it. Make sure you have time. All right. All right, let's talk a little bit about, excuse me, about electric field. Electric field, remember, is the way that charges influence each other through space. In an electric field, electrons, which are negative, would receive a force to the left in this electric field to the right. Protons would receive a force to the right in the same direction as the electric field. And a neutron would receive no force at all. Okay, so neutral objects won't receive a net force. Excuse me. The electric field diagram, vector diagrams, look like this down the bottom right. Notice that X must be a negative charge because the vectors will point inward towards a negative. And for Y must be a positive charge because the vectors point away. And so we know that X is negative and Y is positive, and that Z is a point in space. If I put a proton there, it would receive then a force to the left in the direction of the electric field. And if I put a negative charge at Z, it would receive a force to the right in the opposite direction of the electric field in that region. Okay. So let's see if we can answer this one. So let's read the last sentence. Which of the following statements is correct with these observations? Okay, so what are the observations? It says 3 small droplets of oil with a density of rho. Okay, they just told you that the drops have mass and are situated between 2 parallel metal plates as shown. The bottom plate is charged positive, the top plate is charged negative. So which way is the electric field between the plates? All the particles begin at rest. As time passes, particle 1 accelerates downward, particle 2 remains stationary, and particle 3 accelerates upward as shown. Which of the following statements is consistent with these observations? All right, you'll see the poll that's up. It helps if you draw a picture. Draw your electric field direction. All right, we have a correct answer. Very good. So let me show you. Helps if you draw a picture. It says that they're in between 2 parallel plates. The bottom plate's positive, so our electric field is pointing upward. Okay, and they all have mass. So that means they're all going to have a gravity force downward. And it says that this one accelerates down, this one stays put, and this one accelerates up. Okay, if this one accelerates up, that means it must have an electric force that's up, and therefore it must be positive, a force in the direction of the electric field. Okay, this one is stationary, so that means it must have an electric force up that cancels this one, so it must also be positive. And this one is accelerating down, but unfortunately, I don't know what that means. It could be that it's got a small positive force up, or a negative force down, or it could even be neutral. So it could be positive if it's small enough, negative, or just neutral. We don't know, because gravity is going to pull it down as well. So we're not really sure. Which leaves us with our best answer is that D, particle 3 must be positively charged. All right, excellent. Very good. Okay, static electricity. We're talking about next electric potential energy. So this is just like regular energy that we learned in mechanics. It's electric potential energy instead of, say, gravitational or spring potential energy. Remember that potential energy is the voltage times Q, the charge, all right? Remember that electric potential can be calculated for a point with this equation. That's 1/4 pi epsilon K Q over R, but this only works if you have a spherical charge arrangement because of the radius down here, all right? Equipotential lines, remember those are lines where the electric potential or electric potential energy, if you have a singular charge, would be the same anywhere along that line. So what do we know from this picture right here? So we have two positive charges. I have a higher voltage in closer to the one on the left. So that means the charge on the left must be a higher positive charge concentration than the one on the right. And also remember that if, say, you're moving a charge from point A to point B, that the delta voltage, okay, the voltage difference, that's 100 volts and that's 50 volts. So the change in volts of 50 volts times the charge will tell you how much potential energy you've changed. And if you move it against the direction it wants to go, like if you take a positive charge and move it to higher volts, that takes work. If a positive charge, say, was to move from, so a positive charge would want to naturally move, I'm sorry, towards lower volts, and a negative charge will want to move naturally towards higher volts. So if it naturally moves that direction, that potential energy will turn into kinetic. If you have to force it to move that direction, so like if I take a proton and move it from B, which is 50 volts, to 100 volts here, that'll take work. Okay, so this potential energy you're calculating is either going to be the work it takes to move it there or the kinetic energy it'll have when it gets there by itself. Okay. Oops, sorry. And then remember the connection between electric field vectors and electric potential equipotential lines. The equipotential lines are always perpendicular to the electric field vector lines. Okay. And there's our equation that helps us out, the connection mathematically. All right, so let's see if we can answer this one. The question is, which of the following correctly describes the relationship between the magnitude and directions of the electric fields at points A and B? And then up top it says the iso lines of equal potential are shown in a region of space, and then they show you points A and B in the plane of the iso lines. All right. So see if you can answer this one. We'll give you a minute.
Chris, just to let you know, we're just reaching the hour mark. We're 29 minutes. So
All right.
we're in pretty good shape.
Doing good. Okay, remember our equation for which way the how electric field is related to voltage and the distance between the equipotential lines. And remember which way the electric fields point. They always point perpendicular. and they always point towards decreasing electric potential. All right, let's see how we did. So the answer is D. Very good. So remember that, let's go back to our equation so we can see it. The electric field strength depends on the potential difference and the spacing between the equipotential lines, all right? So notice that we have a 10 volts here and 15 volts here, and we have 10 volts here and 15 volts here, and notice the spacing for the same change in potential is smaller around A. So the electric field will be stronger at point A. And then the electric field lines always point perpendicular to the equipotentials and always towards decreasing potential. So like towards the more negative. So the electric field on the left will be at point B will point to the right, and the electric field vector at point A will point to the left. All right. So there we go. So they'll be in opposite directions and they won't be the same size. All right, capacitors. All right, so capacitors are important for us because in static electricity, because you need to know how much energy is stored on the capacitor. You need to know the relationship between the volts on the battery and the charge stored on the capacitor. And for at least a parallel plate capacitor, that's the only one we really have to know the equation for, that the area of the plates, the bigger the area, the more capacitance it has to store charge. And the closer they are, the more capacitance they have. All right. So notice also on the right, we see the electric field. The electric field always points from positive to negative. And this is how we make a uniform and strong magnetic field. It's all uniform in the middle, all the same strength, except around the edges. It gets weaker around the edges. Okay, that shows up on the test. So here we go. A capacitor with a movable parallel plates is connected to a battery. The plates of the conductor are originally, the plates of the capacitor are originally a distance x apart, as shown in the figure. With the battery still connected, what happens to the energy stored in the capacitor and the electric field between the capacitor plates if the plates are moved to a new distance of x/2? So the plates are moved closer together. Okay, question has just popped up. So ask yourself these things. What stays the same? What has to stay the same? And what's changing? All right. And then look at your equations for a capacitor. All right. We have our response. Our most popular response is that the energy increases and the electric field also increases. Let's find out. So when we take that capacitor plates and we leave it hooked up to the battery and we move them closer together, we are keeping the EMF the same, but we're decreasing the distance. All right. So we're decreasing the distance, so the capacitance goes up. We're decreasing the distance to half, so the capacitance gets doubled. All right. So the capacitance gets doubled, but the voltage stays the same. That means the charge must also double so that the voltage stays the same. If the radius is cut in half, and the voltage has to stay the same because it's still hooked up to the battery, then that means the energy must double. I'm sorry, not the energy. That's the electric field. I'm so sorry. And then over here, if we have kept this the same and our charge has to double, we see that here, then our energy stored in the capacitor also has to increase. It also has to double. Okay, so our energy should have increased and our electric field also increases. Excellent. Very good. Okay, let's move on to circuits. So what we just went through was a super fast review of static electricity. So now let's take a look at circuits. Remember that circuits, we're interested in Ohm's law, that Ohm's law is delta V over R. So the current increases as the voltage increases or the resistance decreases. Remember, current is the amount of charge that passes by a spot in a second, and resistance depends on the shape, the length, and cross-sectional area of the resistor and what it's made of, rho. So that's not density, that's resistivity in this case. There's usually a question on the test somewhere about whether something's ohmic or non-ohmic. So don't make this hard, it's actually really simple. If it's ohmic, then it follows Ohm's law and the resistance is constant. If it's non-ohmic, then that means the resistance will depend on how much volts you put across it. The current will not always be proportional. So if you graph it, as the voltage goes up and the current goes up, if the slope stays the same, then you have an ohmic device. If, on the other hand, as the voltage changes, the current doesn't change linearly, then you have a non-ohmic device. If the resistance changes with the situation, it's non-ohmic. All right. And then remember, power is I times V or I squared R or V squared over R. Now, just so you know, on the equation sheet, power is I times V. That's the only one that's on there. So you have to build these other two or memorize them using Ohm's law. Okay, I suggest you memorize them if you can. It helps out. Also in circuits, things that are super important that you know is these two overarching rules, Kirchhoff's rules, which are conservation of charge, otherwise known as the junction rule. So as current comes around a circuit, so current 1 is coming through the battery and then through resistor 1, it hits this junction at point A. The current splits into two pieces. The current 2 and 3 have to add up to current 1. Conservation of charge. And then conservation of energy is a little bit more esoteric. It's called the loop rule. It's as you go around a loop, the energy that's produced is the same as the energy that's consumed. Okay, so like as we go around the outside loop, loop number 2, the voltage that's supplied here at the battery EMF will be consumed by resistor 1 and resistor 4 completely. They'll split up the voltage. All right, so if this is a 12-volt battery and the first one consumes 10 volts, then the last one will consume 2 volts. In loop number 1, the voltage that's supplied by the battery will be consumed by resistor 1 and resistor 2 and resistor 3. All right, they'll all add up to the voltage of the battery. Okay, so let's apply these Kirchhoff's rules to this question. Which is the correct ranking for the currents for the resistors? So you have different shaped resistors made of the same material, and they're all connected up as shown. There's a lot of distractors in this one. Don't make it hard. All right. You ready? Okay, so there's lots of distractors. We have different cylinders made of the same material. So clearly from our equation back here, they're going to have different resistances, right? However, they're all connected up in series in one line. So Kirchhoff's junction rule says, look, the current that enters resistor A must exit resistor A and then go into resistor B and then go out of resistor B into resistor C. So there's no other place for it to go but from one to the next to the next. So the answer is actually that they're all the same. Okay. So don't make it hard. They all have to have the same current because they're in the same one single line and there's no other place for the current to go. All right, Kirchhoff's rules as applied to series and parallel. Since series is a pathway with many components, but only one pathway, they all must have the exact same current. Okay, and the voltages, according to the loop rule, this 100 volts will be consumed by partially by the first, then the second, and then the third resistor that will consume all the volts. Okay, so the first one can't consume all 100 volts. And then the resistors just add up. Applying Kirchhoff's rules to parallel, we find that in each loop, each one of these has to consume all 100 volts. So the first one consumes 100 volts, the second one consumes 100 volts, the third resistor consumes 100 volts. So they all have the exact same voltage, but they won't have the same currents necessarily if they have different resistors. So the current through resistor 1, 2, and 3 must add up to be the total current that goes through the battery. And the resistors add up as reciprocals. Now, this is important. When you add the resistors up as reciprocals, the total resistance is less than the smallest resistor in parallel. So when I add these three in parallel, the total resistance actually goes down. All right. So just remember that. Okay. So let's apply our ideas of Kirchhoff's rules to this question. It says, what are the currents measured by ammeters 3 and 4? And the information at the top says 4 identical resistors of resistance R are connected to a battery as shown in the figure. Ammeter 1 and 2 measure currents as shown here of 1.2 amps and 0.4 amps. So what do these two read? All right, how you doing? I want you to notice that on the left here, that all the current comes through here and splits up and then splits up again. So, all right. So notice that 1.2 amps comes down and then goes to the right and then splits up between ammeter 4 and ammeter 3. And then from ammeter 3, it splits into 2. And then it all recombines. Notice that these three resistors at the bottom here and the bottom right, they're actually in parallel. So that means they're all going to have the same volts. Therefore, they're all going to have the same, they have the same resistance, so they're going to have the same current. So that means that ammeter 4 actually has 0.4 of an amp, and that means ammeter 3, because it splits off right here, has the current that goes through these two resistors. So our answer is, oh, here it is. Ammeter 3 has 0.8 of an amp and ammeter 4 has 0.4 of an amp. That's a tricky one because it's not drawn the standard way that you would see parallel. And they'll do that to you on the test sometimes. So follow it through and so that you can see, you can actually redraw it. A lot of my students will redraw it so it looks more familiar to them. Okay. Hey, keeping the same arrangement as we saw before, what's the equivalent resistance of the circuit? Okay, they'll ask you to do this in symbol form on the test. So let's see if we can practice it. Remember, the bottom 3 resistors on the bottom right are in parallel. So add them up in parallel. And then the one on top is in series with that parallel set. You can do it. All right. Hey, I think we got the right answer. Very good, everybody. So let me show you how this is done, because I know this is challenging for a lot of students to do this in symbol form. So I've redrawn it to show that these down here are in parallel. Okay, so when I add this set up right here, the equivalent resistance in parallel equals 1 over R plus 1 over R plus 1 over R, which is 3 over R. And so the resistance in parallel is R over 3, or if you prefer 1/3 R. And then that's in series with this. So the resistance in series, you just add them up. So I have an R plus a 1/3 R. So I get 1 1/3. Okay, so let's see if we got the right answer. I'm not sure we did. Let's find out. Oops, I don't remember what the answer was now. Oh, it's 4/3 R then, right? So you were close. All right, keep after it. Those are hard problems to do them symbolically. So you need to practice those, because those will show up on the test. Okay, for circuits, remember that light bulbs, their brightness is related to power, and that the voltmeters are always connected to in parallel, and ammeters are always connected in series. So brightness is related to power. So the brighter the power, or the higher the power of the bulb, of the energy that's supplied to it, remember, the brighter it will be. And then if we look at the right here, we'll see voltmeter 2 is only measuring the voltage for this 100 ohm resistor. And voltmeter 1 is measuring the voltage between A and B. So that would be for resistor 2 and 3, or resistor 1, because they're all connected in the same area. Ammeter 1 down here in the bottom right is only giving me the current that goes through anything in series with it. So that would be resistor 1, the 9-volt battery, and resistor 5, where ammeter 2 is only measuring the current that's going through resistor 2. All right. Remember that real batteries have internal resistance. So there's always a question about terminal voltage. And terminal voltage is just the voltage that we get on the outside of the battery, and we model the battery as it has resistance. I'm sorry, have resistance inside and a EMF of the battery. So the actual terminal voltage is just the voltage of the battery, EMF minus the voltage drop due to the internal resistance. Okay, if you look at that, that's a linear equation. So Y equals mx plus b, that's the voltage at the terminals, equals negative R, the resistance, I, and plus the EMF. And so if you graph that on the y-axis, the terminal voltage, and on the x-axis, the current, you'll get this graph. And so the intercept over here, or the y-intercept, is the EMF of the battery. You only get that when there's no current going through the battery. So whenever they tell you it's a 9-volt battery, it's only 9 volts when it's not plugged in. When you plug it in and it starts drawing current, the voltage drops. And the slope of that, the negative slope, will be the resistance inside the battery. That's one way to find the internal resistance. So if you ever need to design a lab to do that, that's one way to do it. Remember, if there's a switch, the switch changes the circuit. So when I close this switch, the circuit looks like it is on the left. But when I open the switch, all this stuff on the right that was in series with the switch is gone. So it changes everything about the circuit that was where the switch was at. So just redraw it and resolve it for with the switch open and closed. And if you have a short circuit, like if I close the switch down here with these two bulbs, current would normally go through bulb A and B, but then when I close the switch, it's going to, the current is going to bypass bulb B and bulb B will go out. All right, and it's a zero resistance bypass. That's what a short circuit is. So it takes out a part of the circuit. Our last thing in circuits is this thing about capacitors. They showed up in static electricity, but then they also show up in circuits. And the way they show up is they change the behavior of the circuit depending on whether the capacitor is charged, all charged up, or whether it's empty. When the capacitor is empty, it acts like a wire or a closed switch. But when it's full, it acts like an open switch. Okay, so when the capacitor is empty, we get this circuit in the middle at time equals 0. But as the capacitor fills up, it's a break in the circuit. And so this top part of the circuit disappears. And all we have is current going through the bottom loop. Okay, so just keep an eye on that. Just redraw it for when the circuit is full and when the circuit is empty. So this one may be our last question because we're running a little short on time. We'll see. For this one right here, circuit shown in the figure above has 2 resistors and an uncharged capacitor, a battery and an ammeter, and a switch is initially in the open position. After the switch is closed, what will happen to the current measured in the ammeter? All right. Let me give you a little time to think about this one, and then I'll draw it up and show you what it's going to look like. All right, how we doing? All right, so let's see. Let me show you. Okay, so right here, when time equals 0, the switch is closed and the capacitor was non-charged. It was empty. So it's going to act just like a wire. And I'll get this circuit right here. And when I get this circuit right here, I'm going to have these 2 resistors in parallel. And so the resistance right here, the resistance in parallel, remember, is 1 over R1 plus 1 over R2. So that means that's going to be 2 over R. So my resistance in parallel is going to be R divided by 2. Okay, that's my resistance. Now over here, after this time has gone towards infinity, this thing is going to be all charged up. So it's going to act like an open switch. That means this whole section disappears. And that means all I have is this upper part of the circuit with a resistance of R. So my resistance over here is just going to be R. So the resistance has increased. And if the resistance increases, current equals delta V over R. As the resistance increases, and this has stayed the same battery, my current will decrease. So what I end up with is the current here is going to decrease as time goes by. And that's a pretty challenging question. That shows up on the AP exam on a kind of regular basis, but that's a hard question to kind of think through all the steps. So just hang in there and just think through it step by step. Our answer would be it's going to decrease to a constant value. All right. Okay, we have about 5 minutes left. Their magnetism we didn't quite get to, but that's okay. we covered a lot of material in a very short period of time. So I'd like to open it up to anybody that has any questions. Those of you that are at home, I hope you enjoyed the video. Those of you that are here, do you have any questions? You can type them in the chat if you have a question. Okay, I've got a question here. Let me stop share and so that we can just look at us. A question is, how do you recommend we go about studying for the exam in the weeks that we have left? All right. So, well, obviously I would recommend that you have 5 Steps to a 5 book to kind of remind you of what it is that you've gone over. All right. So the biggest thing for you to study is make sure that you're applying yourself in class. That's one thing. Second thing is I hope that your teacher is getting you all the way through the content. That's a big thing. If they're not going to get you through all the content, then I would make sure that you use the 5 Steps to a 5 book to go through the content that you're not going to get to, for one. Okay. Number 2 is, if you've gotten through all the content, then my suggestion is to go through the book and to just peruse through the chapters. There is like some questions before the chapters begin, before the content chapters begin, that give you an idea of what things you're strong in and what things you're not so strong in. Okay. The things that you answer all the questions for at the beginning that are you do really well on, then you don't need to really probably go through those chapters unless you have time. But for the chapters that you had the most questions about, that you did felt weaker in, then make sure you go through those chapters. There's some sample problems in each chapter, and then there's practice problems at the end with a key to help you out. But here's the thing. Go through the questions and struggle through the questions. Read the content, struggle through the questions, and don't look at the answers first. Because if you look at the answers first, you'll fool yourself into thinking that you actually know the content. You're like, oh, yeah, I remember that. But when you have to struggle through it, that's when you actually really kind of learn it, okay? So you don't learn unless you kind of struggle with the material a little bit, okay? So don't be afraid of that struggle. And then go through each chapter that you had questions on, and then take the practice exams, and then see how you did, and then go through the answers at the end, and that will really help. Promise. Okay. All right. Are there any other questions before we go? Because we're just about out of time.
That was terrific, Chris. I really, I think that was a great job. You went over a lot in a short time. I like that ending about the struggle. You know, the struggle's real. Struggle through those questions. That's how you're going to learn the stuff. I don't think I've heard it put that way before. So there's no more questions. We could wrap up a minute or two early.
All right. Well, then, yeah, I don't worry about the physics is an unusual science in the fact that we've all grown up as little physicists, right? We learned when we were little that gravity pulls us down. We learned if we touch something hot, that it's going to burn us. We learned if we fall on concrete, it hurts, but if we jump on a bed, it's fun. You know, we learn all these physics principles. The thing is that most of the things we learned are a little bit not totally correct. And so in our class, we'd have to unteach you a little bit and teach you new stuff. So the struggle is in the taking what we already know and twisting it just a little bit into the actual laws of physics. So don't be afraid of that struggle. That's actually how we learn physics, and it's everybody struggles at least a little bit. So hang in there. You're doing great. And best of luck on your test. You're going to do awesome. Just keep your wits about you. Keep calm and answer the ones you know. and then do your best on the ones that you're struggling with. All right. So hang in there. You're doing great. And I guess that's it.
That's it. Thank you, Chris. Terrific work. Thank you, everybody. Thanks for coming. Take care.